electron configuration for manganese, and that would be, well, let's figure it out. We want to also draw its orbital notation. The best thing that you should look at here is the actual periodic table. And so here's a periodic table, and first thing we got to do is find manganese. Manganese is right over here, and that is, you look at the number over here, and that's 25. That tells you how many protons there are in manganese, and consequently, if the element is in the ground state, then if it has 25 protons, it also has 25 electrons. So we know that we're going to be dealing with Z equals 25, and that's basically telling you the atomic number is 25, or the number of electrons is 25. That is, of course, for the ground state. Now, the reason why I'm showing you the periodic table looking kind of like this is because I want you to kind of envision these colors in your head when you're looking at the periodic table. And what I really want you to be able to do is write down the principal energies and their principal energy levels and the sublevels and all of those kinds of things. Let me show you how it kind of works. You go from left to right, top to bottom on this periodic table, and you kind of work your way across. One thing is that, see this one S over here? I know that helium's on that side, and there's a specific reason why it's on that side. But for now, let's just put it over there as part of that group. I'll move it back later on, basically to show you exactly what I'm doing and why I did it. But let's write down the electron configuration, maybe not just for manganese only, but let's just go and write down as much as we can. So the way you write this out is you go 1s, then you have 2s, because we worked our way to the end of this row, and there's nothing on this side over here, so then we're going to work our way down to the next one. So we're dealing with 2s, and then we deal with 2p, and then we're dealing with 3s, and the next one across is 3p, then 4s, then 3d, that's over here, and then 4p, and 5s, and 4d, and then 5p, and then 6s, and then actually 57 kind of jumps down this way. So at this point it gets a little weird, but honestly I don't think that any of the questions I will ever ask you will deal with going down into that level. So let's just kind of stick with where we're at. What I really want you to do is be able to write down this sequence of numbers by just looking at not this kind of periodic table, because this is obvious, but this particular periodic table. And I'll tell you what, let's copy and paste this, because I'm going to mess with this thing, and I want to make sure all right, here we go. Let's do this, and we'll copy, and you know what, we're going to paste it right next to our thing. Here we go, paste. There we go. All right, so again, what I really want you to be able to do, oh, oops, what happened? Select, copy, back here, paste, and this. Okay, what I really want you to do is recognize that here's the S's, these are the P's over here, and here's the D's. And that 1, 2, 3, 4, it comes from here. 1, 2s, 3s, 4s. So work your way down, and from this you guys can be able to write down this sequence right here. Now, the S's, if everything is full up to this point, then all the S's have 2s on them. because they can accept 2 electrons. All the p's have a 6 on them because they can accept 6 electrons. And all the d's have a 5 on them because they can accept 5 electrons. But in the case that we're dealing with here, we don't have every single thing full. In fact, we're not even dealing with anything past 3D. Because what we're dealing with here is manganese, and you see that manganese was 25, and so it falls into this 3D section. So that 4p, 5s, 4d, 5p, 6s, and all of that kind of stuff, that doesn't apply here because we just need to stop at the 3D. And here's the thing about the 3D is the 3D is not all the way full. What it is, let's see, 3D. Okay, wait 1 second. Okay, 3p6. Shorten it. Oh, I see. The way they did it is they wrote it a little bit backwards. Okay, I guess you can do that. I wouldn't have done it that way. All right. The way the book tells you to do it is they switch these around. As far as why they switched it around, I've never really seen that before. I'm going to stick with going it this way, and I'll tell you what, if I am wrong, I'll make a follow-up video for that one. Anyway, what we want to do is we know that that everything up until this point right here is full. So I'm going to copy this part verbatim. So 1s2, 2s2, 2p6, 3s2, and 3p6. Because that brings me up to, what is this? This is argon over here. Argon, the noble gas. And then over here I have my 4s and my 3d. And I need to start filling things up. So I have 18 electrons accounted for, because if you add up all of these superscripts, so let's see, 2 plus 2 plus 2, 2, 2, 2, 2, that's 2, 4, 6, 8, plus another 6, that would be 18. Yeah, exactly. And then, so what I'm going to do is, I'm going to need to get to 25, right? So if I put a 2 up here, that brings my 18 to 20. And then I'm going to need to probably put a 5 over here. There we go. Cool. And that's it. There is something I did say wrong, and I apologize. I told you that the D's only could have 5 electrons, and that's not true. There are 5 lines that you would draw in an orbital configuration, but if everything was full, the D would be 10, because you can fit 2 electrons per line that you have. Speaking of that, we should probably draw the orbital picture. And the orbital picture would look like this. If we had our 1s, there's 1 line under it. And if we had our 2s, there would be 1 line under it. 2p, anytime you see a p, there's 3 lines under it. And then 3s, there's 1 line. And I'm basically just going off of this list right here. And then there's the 3p, and it's a p, so it has 3 lines. And then there's the 4s, and then the 3d. Now the 4s will have 1 line, and the 3d will have 5. 1, 2, 3, 4, 5. So as you fill this thing up, you need to account for 25 different electrons. So it goes up, and then down, and that thing's full. So we move on to the next. Up, and then down. Well, we've got 4 of them so far. Now the way you fill these things up is we have 3 slots to fill. And it's kind of like, some of you might be homeschooled, so you might not know what a school bus fills up like, or maybe you take the city bus, and so maybe you might have experience there. But it's kind of, I call it the school bus effect, where if you have an empty school bus and you start filling, asking people to sit on the school bus, they're not going to fill up the front row, and then the next person going to sit right next to them, and then they're going to all sit right next to each other as they progressively fill up the back row. No, people kind of I guess they don't like sitting next to each other, at least to start off with. Maybe it's kind of weird if you have an empty bus and someone sits down and then somebody sits in the seat right next to you when they have the whole bus to choose from. So electrons kind of do this thing where they only fill up here, and then if I'm going to put another one in, I put it in the next seat over, and if I fill up another one, it's the next seat over. Now this isn't a school bus, this is maybe a 3-seat car, or let's say a 6-seat car. So you have this seat over here, and you're putting another one in. Now this other one, this 4th electron, doesn't have any choice but have to double up, and so now he's going to fill up over here, and then the next one coming in will fill up over here and over here. So how many do we have accounted for? We've got 2, 4, and an extra 6, so that's 10 electrons so far. So then here's my 11, 12. I've got another p situation, so I've got 1, 2, 3, 4, 5, 6, and I think I'm down to 15. Or, well, no, let's see. It should be 18. Let's see. 2, 4, 10, 12. Oh, yeah, and this is an extra 6, so that's 18. And then 19, 20, and then as far as this 3D filling up, he's going to go up, 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 and up. And I'm not going to put any downs in there because I don't have a 6th one. I'm done at this point because I've accounted for all 25. Now, as you do more and more of these, if I asked you to do, let's say, 29, and what is 29? 29 is copper. If I asked you to do copper, you would find that see, all of this stuff over here would remain the same. You would go through this whole exercise and you would do the first 18 electrons, and then they would all be the same, and then anything in this row would have a different number of things that in there. You would probably add a 4p onto the end of this thing if you started doing like 33 and 35 and that kind of stuff. But what you're going to find is that the only thing that really changes is this over here. So we kind of say, well, we can lock down this thing over here. And the way we shorthand that is we know that this 18, what is that? That's argon. So what we say is if we want to do a shorthand version of this, we just say, all right, well, assume that you have the electron configuration of argon, because that brings me up to this 18. And then I want to add to that, because argon was here, right? I want to add to that the 4s2 and the 3d5. You can do that for the orbital notation as well. You just say, all right, we're going to assume argon over here. And then I want to add to that a 4s shell that has an up and down, and a 3d shell that has an up, 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 and up. All right. Well, I know that was a lot to take in. I hope that helps.